El director de la orquesta. Okay, are we ready to go? Perfect. Thank you very much. Welcome to the second day of presentations of the Capstone Project. We also welcome those who are connected online, either at Zoom or at the YouTube channel of DigiTwins. Today we will be receiving the presentations of 3 projects. Very interesting projects. I have had the chance to review some of the presentations, and I can anticipate that you will certainly enjoy and think a lot of what they will be presenting. The first one is on digital twins applied to dams. Second one is relative to the optimization of the bicycle service in a city like Barcelona. And the third one, the Eventful, is on the application of artificial intelligence and machine learning techniques to the evaluation and optimization of the impact of events in cities like Madrid. So a lot of things to do. We are a little bit late. Try to be short. First one is a presentation. It's a Capstone Project which has been developed by these young guys that I will have the chance to introduce now, and has been supported, defined, and mentored by AGESA. We can be more thankful for the support that AGESA has delivered to the project, the master, and the team from the beginning. This is a perfect example of something or a reason why AGESA believes in this project, because there are clear applications of digital twins to their field of development. And in fact, you can tell and how this development can be directly implemented and applied to assets that you already manage. For that, I would like to thank Fidel Sanemeterio, who's connected online. I saw him around. Carlos Rodriguez, who's here with us today, and Luis del Castillo, who have been mentoring, supporting, and leading the project. On the side of coordinating, we have had also the pleasure and the honor have the coordinating supervision made by 2 absolutely respectable and professors of the universities of the Civil Engineering School of Madrid and the Industrial Engineering School of UNED, Eduardo Salete and Miguel Ángel Toledo. Also, my thanks for their support to Eduardo, who is here with us listening to the presentation. And finally, I would like to thank and congratulate. I say congratulate because I have already seen the presentation, and I know that you will enjoy it, as I said, to the whole team. To Ivan, to Ángel, David, and to Luis, who unfortunately could not make it today. Hope you get better, Luis. And we were absolutely certain that they would do a great job since we formed this group. They link very well together. Beyond doing a great work, I think that you have done a very good and solid friendship. So let's go forward.
Hello, everyone. Development of a done digital twin for safety management and operation is divided in 6 parts. 14 an introduction, And as I say, digital twin implementation, big model development, physical model development, database model development, and work planning solution. The working, as I say, David Cuenca, Dan Campos, mi madre online, and myself, Miguel Ángel Toledo, Eduardo Sabete, de Academy Supervisor, y del San Emeterio, Luis Castillo y Carlos, Company Supervisor. Thanks to Confederación Hidrográfica de Guadalquivir, and Aliesa for the support and this project. Digital twin dance. The implementation of digital twin dance infrastructure is revolutionizing the way that critical assets are managed and maintained. The implementation of the concept of the digital twin as a virtual replica of the system, the dam, reservoir, basin, and river, will be of great help in the operation and maintenance of the dam. And will be able to determine in real time the responsibility of the dam, not only on the real monitoring scenario, but also to other possibility scenarios, make predictions and implement. Setting aside on the possible data acquisition of the monitoring data, present of the dam data software. Implement a virtual machine to integrate and qualify data storage, server, web server, buying model, field server, field client, physical model, and database.
Well, in this graph, you have an overview of what can be a digital twin of a dam. And in the central core of the digital twin, we think about a model. The model, if you have sufficient data, you can develop a database model. But in general, in dams, we don't have enough data, so physical model is usually mandatory. In those models, you need some input that usually is stored in a data center, which is in this case integrated in the virtual machine, which we integrated all the digital twin. And this data also requires a geometry of the dam or the reservoir or the basin, whatever you are modeling. And every one of these inputs come into the model, and then you can have some results. Those results could be initially not well calibrated, so you need some kind of calibration or validation to get the real response of the dam. The digital twin could be in several elements of the dam, not only the dam itself, but you may need also the watershed, or the reservoir, or even the river. For example, you can make a model, an hydrologic model, or you can make a model of the flow of the river downstream the dam. So this is a general overview.
Models development. By model, physical model, and database model.
Those are the models that we are going to develop in this phase.
By model. The by model of Daniel Dam will be updated to consider as the only thread is the physical and database model. Define a structure for organization. Physical model. Physical model will be developed to prove the capability of such a model to reduce the expected mechanical behavior of the dam and compare it with reality with data captured for the dam monitoring. Database model. A database model will be developed to prove the capability of such a model to reproduce the measurement captured by the monitoring of the dam.
So initially, the data acquisition of the dam, we try to connect our digital twin directly to the dam. So in the dam, usually the data is captured, for example, from the monitoring of the dam. This goes to a PLC, and then from there to an SCADA, that is a computer in the dam. And this is data is then transmitted to the headquarters of the Confederation, Hydrographic Confederation of Guadalquivir, where they have a program, a software that is proprietary, that is called dam data. And we try to connect to that. The Confederation gave us access to this software, but the data acquisition needs to be manual. We try to do it automatically to incorporate it in real time, but for problem of security and safety, they didn't take that. So in our digital twin, we need to insert the data into the Microsoft SQL server that we implemented there. We created a digital twin platform, which is composed of a virtual server, a Windows server, that integrates Microsoft SQL Server 2022 as a central database. Also, Internet Information Services. Also, we implemented a QGIS server, a QGIS web client, Grafana for data visualization. The BIM model can be stored in the virtual machine, but at this time we cannot visualize them. And a contact for Python automation of all the physical model calculation, and also for the database model that we did. And a web platform that is being developed by IESA, but is not included at this time in the platform. So, Luis?
Okay, good morning, everyone. Sorry to not be able to attend, and I hope you hear me correctly. So, like my colleagues explained, we generated a BIM model for the dam was one of the first steps of the use cases that we defined for our digital twin. So, the creation of a BIM model as part of the digital twin aims to obtain a real digital representation of the built asset. With that a model that represents the physical reality of the built asset with the real geometrical dimensions and their physical aspects to be better represented, to serve as the visual layer of the visualization layer of our digital twin. This BIM model will not only support the visualization of the asset, of the real asset that we are wanting to manage, but also to support the integration of all the different data and also the physical model developed within the digital twin system, allowing to connect each element of the data collected by establishing a direct connection between the built element and the real data through the data structure defined of our digital BIM model. So to fulfill this objective, we defined a model that Thank you. Sorry. So to fulfill this objective, we developed a technical design approach to define each element specifically aimed to fulfill the use cases that we wanted to develop according to the technical specification of the built dam. So the basis for this, what would be the normal process would be to acquire a digital point cloud of the assets in order to develop the BIM model. For our part, for our work, we did not have access to the point cloud of the Dañador Dam, but we did had access to an initial BIM model that had already been developed by the Confederación Hidrográfica de Guadalquivir to develop as a pilot for digitalization process of this dam. So we use this initial BIM model. This is the one that we are visualizing here at the left lower side. So we use this initial BIM model as it was a point cloud. So it would define the overall geometrical dimensions of the dam, so we can use to develop our own BIM model. So the first thing that we encountered when analyzing this model, we encountered two basically problems that we needed to correct and define to develop our digital twin. So the first one was the geometrical representation. As you can see in this model, the model had very, very big errors geometrically. So it was basically very simplified in the way they modeled the body of the dam, because it was only represented by two basic big blocks that all overlapped over one another. So this did not allow us to visualize correctly, and not only to interpret how the dam really functionally operates and how it was built. So this was one of the first things that we needed to correct. So the geometric reality of the dam was not correct in this initial model. The second one was also how the information was organized within the model. It was basically only one model with all the elements inside. There was not a clear data structure defined for the model that we can use to map and integrate within our system in order to connect with all other data sources that we had available and that we wanted to connect in the digital twin. So can we jump to the next one? Okay, so the first step was to correct the geometry of the dam. So we used for technical information of the technical archive of the Daniel Dam that was provided by the Confederación Hidrográfica. And the first step we did was to model the complete body of the dam from scratch, defining each of the blocks that compose the main body of the dam. This does not only allow us to define correctly the geometry that later would be used and will be the base to develop the physical model that Ivan will explain later, but will also define correctly how the asset really is built and also to allow us to locate some of the aspects and to connect some of the aspects of the visualization of the asset. So some of the data that we are going to integrate is sensors, and some of these sensors are directly correlated to the position of the points of connection between between the blocks of the dam. So it was very important for us to have that information within the model. So when you're visualizing one sensor that is giving you data associated to a specific point within the model, you can have that information by which area and to what elements we are correctly giving that reading of the data. So this was not only a geometric operation for dividing physically and to model physically each one of the blocks. Also, we characterized each of the blocks with a tag identifying which of the blocks there is. So to start defining this data structure within the model. Another aspect that we did also to connect or to integrate the BIM model to the physical model that we're going to be developing was also to define the different layers of materials that we could, with the information that we have from the technical archive. So we could have a different layer of concrete from the inner block and to the outside layer, because this is also important and is basic information to have for developing the physical model. Can we go to the next one, please? So this was the geometric side of the development of the BIM model. Another aspect that we did was also to define the data structure. So the first step was to separate and identify clearly each of the elements by the type of elements. So this is as a BIM methodology step. So is the federation of the models. This would just allow us to give a first layer of definition of data structure. So we can have different models that can be directly connected to the elements according to the type of the elements. And the second one was to define a data structure with parameters, with data that we could connect and that we can integrate to each of the elements. So for example, on this table that we have right here, this is the list of the blocks of each of the elements of the civil of the structural elements of the dam, when you can see a description, an ID for the location of the elements, the type of the element, the small description. And also one thing that we included in this is in the data set was we classified all the elements according to Uniclass classification system. So this Uniclass classification system was just is a standard classification system that allows us to identify by a code each type of the element. To allow us to give us another step of granularity of the information that we had available within the model. Another thing that we did was also to connect the data by reading the table that is below is a part of the data set for the readings for the sensors that we have installed that we have connected from the DAM data. And so what we did was identify the codes of each sensor that we have here. and also the readings of the basic information of the sensor that could identify us the position of the elements, the location, and use this code of the sensor to integrate that information within the physical elements that we modeled for each of the sensors. In this way, this would allow us to physically connect and by the information that we have within the BIM model to the data set that we want to visualize to give us another step in visualizing data in an integrated way between the different databases. Can we go to the next one? So, like I said, this is the final visualization of the BIM model of all the integrated different type disciplines of the federated model. And in the left, what you can see are the basic geometries that represent all the sensors and all the installations that we had located within the BIM model. So you can see that the sensors are located within the galleries. Each of the sensors has their own information regarding the position, if it's in the lower gallery, to which block it's associating. This specific one that we are seeing right now, it's a vibrating wire piezometer, is an so this allows us to, once we can integrate the visualization layer of the BIM model within our digital twin, to select this element, filter out the information, and connect this physical elements with the data set from the readings, and also allow us give us a greater integrated vision of how the asset is behaving. Yeah, that's it for my part.
Okay, now I'm going to describe the physical model that we developed. The physical model, as I said before, is the model itself is performed in Fluxys Connect Ultimate version. The model is done in a section in 2D that was extracted from the BIM model that we see, and I did an elastic model for simplicity, and also because this kind of terms are very appropriate for that. The model needs some input, the geometry, as I said, that is for the BIM model. It is the load. The loads are the reservoir levels over time, and also the temperature of the atmosphere over time. Also, you need to define the material. The materials are defined from the document in the technical file of the TAM, but this information is very small, and so the only data that we have is the cement content of the concrete, and also some geomechanical stations in the foundation. The model will give us, as a result, the movement of the ground of the dam, which we are going to compare with the measurements done in the monitoring system. Initially, with this configuration, they won't match, so they need some kind of calibration. And all this process is automated by Python using a Fluxys library. So the final aim of the objective of this model is to replicate the movement in the crest of the dam. The geometry is taken from all the sections in the block that Luis identified, but in this case, we did only the central section, but it could be extended to another section easily. The loads are taken from the monitoring system, are daily based in a range of 15 and 13 years. Also, the temperature has the same range. And the material, as I said, I was taking from the technical part. The implementation of the final terminal model is done in Fluxys. It needs first the model creation. You have to define the geometry. Then you define the material. You assign the material to the geometry, which is defined by polygon. Also, you need to implement two phases, an initial phase that takes into account the construction of the dam until it's finished. and then a transient phase, which takes into account, in this case, the range of measurement that we have. Then you perform the model calculation, and then you get the result in a form of a curve over time. This is fully automated in Python. The Python model is composed mainly in a class that is called class system. The class has several properties that are needed to define all the data that need to be input in the model. And then it has several methods. The methods are used to incorporate information into the object, and also to calculate, also to calibrate, and also to get the result. So the main program, first we need to define the input. The inputs are, in this case, included in the program, but the objective is that this data can be taken from the Microsoft SQL Server. From the Microsoft SQL Server, we take the monitoring data and for the loads, the server levels and the temperature, but also on the measurement of the ground movement. Then you need to construct the instance. So you make a Flagsheet object with this class. You need only the server configuration of Flagsheet server Flagsheet configuration, and also the Microsoft SQL Server config. In this case, you have an empty object that you need to fill with the data of the model. So first you create a new model, and you include the new geometry with those methods, then define the material, set the material to the polygon, mesh the model, then set the phases that I explained before, and some data like initial temp of the material, also the head function that defines the water level over time, and also the temp function that are for the method. And then you calculate it, and then you get the result. And with the result, you optimize the model. You optimize the model by changing the parameters that we selected, that are the elastic modulus of each of the three different materials that are in the dam, two complete materials and the foundation. And then, in this case, we perform a nonlinear optimization, and this was the initial configuration. But I indicated, this is the document that we sent in July, but we detected three problems here. One is that the foul boundary condition. Oh, sorry. The default boundary condition of the traffic was time the foul put automatically the top of the model. So you needed to put it manually.
Ivan, we can't hear you.
Sorry?
We can't hear you.
Can you hear me?
Yeah.
So you have to put the boundary condition of the temperature in the surface of the foundation and the dam. And another problem was that this optimization, nonlinear optimization, was very slow, because it needs for every iteration to perform a model calculation, but also to define the Jacobian of the Jacobian. So you need to define gradients that need at least two calculations for each of the parameters that we need to optimize. So in each of the iteration, we need 5 model calculations, so it takes a long time. Another thing, I don't know if they want, I don't remember the day one, so I have to continue. So what I did, I solved all of this for the delta function in Flagsheet to assign the temperature boundary conditions. So I did that, but I found the problem that so the Flagsheet reference manual said that that was implemented, it wasn't. So when it couldn't be fully automated because of that the Flagsheet empty. And the other thing is that this is a linear problem because it's elastic, so we don't need a nonlinear optimization. So I formulate an elastic linear optimization that only needed 5 model calculations. With 5 model calculations, I could calculate this. So this is the result of the physical model. Initially, with my definition of the material, you have here. You have here the measurements. You have here what the model gave. The difference is because the measurements usually start from zero, but in reality, if you take into account the construction, you don't reset because of the formulation. You couldn't reset the displacement. You don't reset the displacement at the end of the construction. You get a lot of difference, but also the amplitude was so small. So you need to calibrate the three elastic modules, but also the initial movement. And when I perform my linear elastic optimization, then we match the real measurement with the blue line, and we get these calibrated parameters. The parameter calibration, we take a bound for not getting unrealistic parameters. So, for example, this is, for the elastic modulus, I set a bound of 1 order of magnitude, and for the foundation, 2 order of magnitude. We get these parameters calibrated, and when we include in Plaxis, we get the green line. The difference need more research because I don't know why there is so high difference between the manual calculation. I didn't say that I need to do this manually because of the boundary condition in Plaxis that I couldn't continue from that. So these are the results of the at the end of the model, the temperatures and the movement, vertical movements at the end. This is calculated along order range time. And more work to do is to implement this in all the sections of the dam, so you have more data and you can calibrate everything together. Also, the horizontal movement, I did this only with the vertical movement. And I think I'm going to pass. So the data is not
Okay, thank you. Hello. Now is continuing the work of my house. We're going to talk about database model, and we try to adjust. Okay, this is the data that we are going to explain how this data model built, and this is the steps that we have to follow to build a data model, data collection, data processing, exploratory data analysis, model selection, model training, model evaluation, a refinement of the model, and finally an implementation. The data shown in this table is the data that we have from the SCADA system of the Confederación the local authority. And this is the data with a date and the name of the sensor, the lecture, and we have filtering for every sensor. We have all the measurements of all the parameters of the dam. The data collection, the first step is to gather historical data for interstitial pressure at various points in the soil of the base of the dam. We have 6 piezometers to measure the pressure, and also the filtration on the dam is also measured by 3 sensors. So the main data that we have is the one here. This is the water level of the dam. We have this is collected daily. We have results for 12 years. So we have a lot of information of the level of the water of the dam. The second graph is the pressure at the bottom of the dam. We have 3 piezometers. The data is collected for 8 years, but twice a month. So that means we have less than 200 data. So this is a challenge to try to fix a model with this few amount of data. the next step that we should take is in the data, removing outliers, inconsistencies, and normalize or standardize the data. Here, for example, is an histogram of the 3 piezometers. Down, this one is a correlation matrix between the level of the dam, the level of the water of the dam, and the pressure of the sensors. For example, it's obviously that the level of the water in a dam is related to the previous level of the water of the dam the day before, for example. So we build an autocorrelation of NEMBA. NEMBA is called the level of the dam. Here we can see that there is a high correlation between these data. We also can have a time serial analysis of the data. That is the graph here. So this graph that we can see here can be decomposed in these 3 graphics. 3 graphs. This is a trend. This is a seasonal component, and this one is a residual. So we can try to build a model that minimizes the residuals and try to fix the water of the dam in a time series. So to see that, we can use this scatter matrix that show us the water of the level of the water. This is 1 piezometer, another one, and these graphs are the relationship between all the variables. We can see, for example, the number 4. This one has a good correlation between the level of the dam and this one. Here you can see the data more dispersed. And also to see how is the data analyzed, we can see a box plot that show us, for example, this is the 3 piezometers. They are quite correct data. You can see there is a different mean pressure, 1, 2, and 4. The data is clearly adjusted to this value. And this is, for example, the rolling mean of the original data. Here we have in the step 3, the step 4, we need to select a model. Which one? We don't know. We need to play with the data, try to fix it. So we can choose an appropriate modeling approach. First, a linear or polynomial regression. You can see a graph like this one here at the top. Time series analysis, for example, and here you can see this big graph here that shows in every row we have, this is the level of the dam, the composing trend, seasonal, and residual. If we do the same with all the pressure for the measure, we can see that the trend is really similar. Makes sense. The seasonal is fairly similar also, and the residual change a lot. So we are going to minimize the residuals and try to correlate these values. The next approach that we can say is we can use is a classic machine learning model. So we use linear regressions, key nearest point. Okay, the most common, and to see how these models match, we can plot it in this way. So the higher this box plot is, the better the model fits the data. And also, if we have more data than the one we have, we can choose some other neural network or a LSTM model that, for example, we built one, and this is the adjustment. It's very poor adjustment. The 5th step is to train the model, so we can build a table like this one. We can choose some methods to evaluate the data. The data is R square, RMC. Here are how every model how can fix the data. Then the step 7 is the model refinement, and the step 8 will be the implementation. So this is how we can build a model. So let's see 2 examples. Let's apply this to the pressure module. So we have the beginning the data, this data, and we need to find the relationship between this pressure and the water level of the dam. It's quite different, the curve. So, okay, we put here the distribution of pressure. That looks quite good. And so we try to decompose, as I told before, in trend, in seasonal, and into a residual. So we need to make this decomposition, we need to set a period. Which is the best period to decompose? I don't know why, which one. So I adjust this hyperparameter from 4 period to 24. This is the adjustment. So the best one is 6. The training is, the model is adjusted in a 0.95. That could be this training set. And the adjustment, and also MCE variable very low. The lower this value is, the better the adjustment could be. And testing this model give us this graph that I think it speaks very well the values of the pressure of the dam. This is the 8% of the data, and this is the 20% of the data. Always talking in a time period. The first, if we put a line like here, we can say this graph could be this graph, and this one could be this one. Okay? The best model that fits the data is a random forest regressor with these parameters. Decompose it, the trends, and seasonality, a residual, and a period of 6. Let's talk about the filtration. Doing a similar process, we have this data, pressure, we have the distribution of the data in this histogram. I print here a box plot of filtration. This graph shows us that there is a lot of outliers. Outliers are data out of the typical margins. So instead of cutting these values out, just working with that one, we use a model that minimizes the effect of the outliers, but keeping all the information, because if we only have 200 values and keep all the values out of this margin, it will be a problem. So we use a XGB boost regressor with a data win solution at 5%. We put 2.5% upper and lower, and try to fix how it works. So this is adjusted quite well. The 8% of the training set and the 20% of the test system is this one. These are values out of the. We don't know exactly why these values are, but the filtration of data should be aligned slightly like this one. And with that, I finished the part of the database model, which is two examples. So, okay.
Work plan, schedules, and cost. We have four main phases: start of the project, project development, project integration, and data management and maintenance. First, we would like to commentate that there are activities planned that could not be carried on in the project for several reasons. This reason, as for example, inability plan, drone plan, lack of maintenance work by the or over-optimism in the initial planning of the Capstone Project. geology and geotechnical study and testing structural. These are also being designed to lead them in the planning for future improvement and adaptation for hypothetical plans. The start of the project is divided into two main project parts: the starting documentation and the research project. The organization of the BIM model is the main activity that will start at the beginning, on which to direct the activity is Cascada or is in compliance. Investigation has been grouped into six divisions from plan modeling and geotechnical geology and the structural test study of the structure. The development of the project, which is productivity, integration platform, physical string, integration test, and associated results, geometric and information modeling, data acquisition, and functional model, will be the next activity to this area. This session online the timeline for completing the project, including the goal and the the estimated cost of the project is 356,000 euros, with significant extensive allocated sensor and server database development. Biometric sensor and taxes are 57,000 euros, and server and database development at 80,000 euros. The cost reflects the investment made implementing a digital twin and new center, its functionality and reality. Monthly expenditure is estimated to average around 56,000 euros, during a peak in the 4 months due to the sensor installation. This peak expenditure is necessary to keep the dam with the recurring sensor and monitoring equipment. The careful allocation of the funds ensures that are critical components and coverage without extending the budget. The cost estimate are based on experience, project and contract with supplier. It provides a relative view of the financial requirements to help in planning and resource allocation. Accurate cost estimation is crucial for project feasibility and ensure that the project can be completed within the allocated budget. The project timeline and budget are designed to ensure efficient use of resources by planning distributed helpful and monetary response regularly. The project can evaluate the dimension around and ensure that unnecessary activity are prevented. This financial planning is essential to the project function. And this is the end.
Thank you, Luis. Thank you, Luis. So now it's time for
I have two questions. You have generated 3 models as a base for digital one. The dam development of the dam digital twin for safety management. This is the title of the project. But if you say this is a digital twin, are these 3 models a federated model is not to run the digital twin model of the dam? So how they communicate with each other? But if I have a digital twin of the dam, so these models communicate, for example, if there is a high level of the water, indicates that communicate with the other physical models, saying if the sun shut down the power or shut down the, how did they communicate? I didn't get that point.
These 3 models are integrated in this platform, the virtual machine platform. So the physical model is inside this platform. You have the result from a Microsoft SQL server that has all the data integrated. The aim is that we take the data from there to get into for the database models and also the physical database models. And the results are also included in the database. So In our case, this order is integrated. The VIM model also they pass the geometry to the physical model. So the link between the BIM model is that you can get the geometry to define what you need in terms of geometry for the physical model. Another thing is that a physical model can also be used once implemented like this to fit database model, because the database model has a problem that the data is very limited, no? It is a problem that you encounter in the
Very challenging.
so you can generate more data to test faster models, for example. In this case, also the final objective of the BIM model is to include it in the web platform so you can visualize in 3D the data, and also you can get alerts that are getting from the database model and also from the physical model when some of the monitoring parameters, for example, get out of the what is expected. And you can visualize, for example, with a red point in the BIM model. So this is being implemented, the web platform is being implemented in AGESA, so it's outside our scope. At the end, it's the final objective of our fit that is all integrated. So we have here, for example, GIS model, not only BIM, this model gives you 2D representation of the dam, the reservoir, the watershed, and you can also visualize also the results of our model there. That's also the
When you model, actually, I'm looking for artifacts. To make sure the parametric BIM model as a physical model. So all the actually, when we say BIM model, it's a parametric BIM model, and we don't distinguish that like as a physical model. If it's dynamic BIM model, it's a parametric model, which you call it physical model. That might be different with Bentley, maybe Bentley.
like a BIM model doesn't have a model of behavior, for example. You can model anything there. You only get results. You reflect. Luis can also. Luis, can you hear?
Yeah, I didn't hear the question. So
You perform calculations in a BIM model, no?
sorry.
You don't perform calculations in a BIM model that gets results like the physical model that I developed, no?
It really depends on the software that you use. You can run small calculations, structures, and also for systems within a BIM model. Revit model does allow that, but it's not the tool to do it because the results are not correctly calibrated. So to run a calculation for a physical model for structural calculation or whatever, it's always better to use. We can use the geometry of the BIM model or the information that we have of the BIM model as a base to run a calculation, but we need to use the correct tool, specific software to run that calculations to ensure that the result is reliable.
What I mean by physical model is a model that is based on physical properties of the dam. The basis of the data, the model is based on physical features. You get physical parameters and you get results. You can get results from a small amount of data because you have a model that you know the behavior of the model because it's based on physical concepts.
Target of BIM model is the physical model aspect. Not yet developed.
We cannot hear anything.
Okay, the ultimate goal of the BIM model is to be actually physical BIM model, not the dynamic only geometric model.
It's like a final objective.
Yeah.
Work, a very thorough methodology, especially for the data manipulation, cleaning, and the refinement of the model. I really appreciate that you have made the business and money implications regarding the sensors and
setbacks and other technical infrastructure that is needed. This is very important. And I have a question regarding that. What is your opinion? So now just what are your thoughts regarding the integration of the world of Internet of Things? Because that can transfer data into the internet, and you know its identity, its Internet of Things device, your project.
Integration of the, I think a key point. It's a key point of this one to have all the data from the dam, from the dam, but we have a problem with this data, that is the problem of the ground water. It means that the water level taking daily, automatically, send it daily, and the data from the pressure filtration are collected manually twice a month. So it could be perfect to have all the data maybe daily or even hourly. If we have thousands or millions of data, we can fix a model perfectly with the data. Just now, it's only 200 data. Try to fix the last 40 using the first 106 to be the 80%. So predict the 40 data in a hard work. Okay.
What is the personal contribution of each member kind of project?
In the case of Luis, is the VIM model. In my case, is the physical model. David is the database model. And for time. Differentiated.
Congratulations, the brilliant project. You explore all the aspects. So, but it's very nice to see now.
Try just to try. But can you close the microphone?
Okay, yeah, I had a no. It's too much.
Speak louder, maybe we can.
I have a question. Person of the physical models, the models. Is it fully automated or we have a problem when you take the space of the geometries from the physical model where you don't have to connect lines and then you have some kind of manual
The connection of the VIM model. Luis implemented something that takes sections on each block.
Sorry,
Luis?
I didn't hear the question.
Luis, he asked about the connection of the VIM model with the physical model, how it is done. So I said that you perform some sections of the VIM model that is done in each block. And then,
Yeah.
and then
Yeah, so sorry, yeah, the connection, in our case, we used basically the sections that we extracted from the BIM model because the type of physical model we needed to develop, we did not need the 3D representation of the full of the blocks. So we used only the sections of each block to calibrate the model. But Ivan can explain better the physical model.
the link is not fully automated, because you have to take the AutoCAD section. And what is done is that you define in AutoCAD the polygon. The polygons are composed by points, and each point you have to take care that they don't repeat and everything. And that is put into the Python in a form of um, a list of tuples, a list of points which define the polygon. This is the variable that you include in the Python code. So you need to pass from the section to this list of points that compose each polygon. And the boundary condition is a list of points of the polyline. And that's it. I think, well, the point of the crest, also you have to put it like a point. So yes, a faster work might be to automate, to simplify the section that we escape and to convert the DWH file to this list of points. That's normal.
Modo presentación.
Que no se ve, ¿no? Ya, pero que no se ve.
Can you comment on the values obtained on there? Are the values, the calibrated values realistic?
How I get the values or
How do you the values that for instance, the young
your modulus of this is the your modulus of complete of a component of 250 kilograms per meter of composition of the stone. And I calculate the your modulus of the component of the tension and the calibrated value. Okay, this is the calibrated value of the your modulus is 2 times this. This is 10 times this. This is 100.
What we do is that we have to provide
the first column is calibrated.
This is foundation.
Yeah. And in the column, the calibrated get like 200 gigapascal. Yeah, but you comment on that. You cannot just expect to calibrate the model based on physics and out of some values that are, we all know that are not physical. So it means that you are calibrating a model with maybe insufficient number of parameters calibrated over your model. Maybe you need to account for support conditions or other parameters like non-linearity. So you said that you have some limitations in the calculation, but this is not.
Well, what happened here is that we have you said I have to be careful with the presentation.
Yeah, you have to say is that the calibrated values are do not make any sense because we don't have enough.
Maybe I have to put some bounds lower than I did this in one day, so it will go a little fast. So maybe around not 10 times to another time, or something like that. The problem here is I reach 10 times because this concrete is only this part of the surface, so and it is sensitive to the surface. So I can get 10, I can get 1.
Makes any sense.
If you have more points, then the evaluation. We have only these points that I think or something like that. I even didn't do the evaluation, so we don't do the translation. In the future, as I said here, you will need to do more evaluation.
Thank you.
The third problem that I found is that the latency coefficient of is very sensitive. So I need to put it like an additional parameter to for that.
Okay, we are running here. Thanks, so we should move on. So thanks again. Thank you. That's the time that we start.
Es normal.
Thank you.
Es normal.
So we have to do it quickly. So you can put it, we don't need, you can put it normally on the other side.
As we can only use one just.
We have to do it. No consigo el micro. Sí, el micro. Do you have an assistant microphone? This is for the microphone? Yeah. No, that one is for the remote. One is for the remote.
What kind of form?
Yeah.
HDMI, yes.
Bueno, lo cambiamos como de ahora, es que está preparado.
Bueno, espera, que saque lo mismo que ponerse aquí. Es que para cambiar, yo creo que se ponerse aquí. A ver, cambia ahora. Sí, pero claro, no sé, digo que claro. Si pones el ordenador
No, put it in screen. No, no, o sea, es más el mando. Which is the problem? Claro.
Ahora pues el micrófono. Voy a compartir la pantalla y
Share it in big, put it in big screen. Start the, and now is it working? Is it working or not? Yeah, it's working, it's working. What are you doing? It will get, it will, no, if you don't touch it, maybe it will disappear, no? Ocultar controles. Ocultar controles de reunión total.
No?
Yeah, but you need to put the focus. Is it working? If I, wait. But it's not working with the.
Yeah, it's not working.
Even with the keyboard.
No, it's not.
Now it's working. Perfect.
Yeah.
So you have to speak in the microphone. You can give the. You can give it or you can keep it.
Because it's for the Zoom as well, or it's for this?
It's only for Zoom. Only for.
This is for Zoom.
Only
Okay, okay.
But you have to give it.
Yeah. Okay.
You speak. We are talking.
Well, hello everybody. Let's start because we are in kind of tight schedule this morning, please. So you already know me, but I've been my name is Alejandro Fedaque. I've been the coordinator of the Capstone projects, and I'm so happy to present the next Capstone project that it has been a collaboration of 3 entities. UPM in the form of Natalia Sobrino, that has been one of the academic supervisors of this Capstone project. Also, I would like to introduce Juan Benavente, that he is visiting UPM, but he's a professor of Universidad de Cantabria. And also, I would like to thank the support of NOMON in the form of Javier Burrieza, that is here, but also from Oliva, that has been collaborating with us from the very first beginning of this master. For us, it has been quite interesting to do so, because one of the main keys and the main objectives of this project is not only to teach students, as Alberto and Ivan, how to develop digital twins, but also to establish connection lines and communication among universities and companies. So for me, it has been a great pleasure to collaborate again with Javier, that he is a former student of UPM, and it was great to see that the connections that we had some years ago were still available and fruitful for both the companies and also the students and the university. Apart from that, I would also like to thank Nomon again, because he himself and other mates from his company were ready to help us when we had some problems in the next Capstone project, and they were so available and so happy to collaborate again with us and help us. So I would like him and also all the team from Nomon, Oliva included, to thank them really deeply with this. In the next Capstone project, what we are going to see is the development, how the mobility can be modified and analyzed in a bike sharing system in Barcelona that has been developed by Alberto Navas and Ivan Revilla. And I hope that they are ready to do so, because in the very first minutes they are going to do so. So thanks a lot, everybody, for being here, and I hope that you have a lot of luck.
Okay. Thanks. Thank you, Alejandro. So thank you, everyone. As we are a bit like behind of schedule, I'll try to speed up a little bit. So as Alejandro already introduced us, I'm gonna be just quick. You see here the content for this presentation today. So the very first point, it's already done, so I'll be really fast. And then I'll talk about the objectives of this Capstone project, focusing on the main objectives that I'd say that is more the commercial side of this project, and then the technical objectives related to coding, programming, and how we interact with our, let's call it, application so far. Then I'll explain a little bit about the methodology followed just to develop this digital twin, and then I'll pass it over to Alberto to talk about the digital twin development itself, everything related to the technical background, and then we'll explain the results and the outputs, and Alberto will perform a little bit of a demo for you. It's going to be the premiere for this app today, and then we'll talk about the conclusions, the main conclusions, and how we could move forward or just scale up this application in the future. Who knows? So the team here, as Alejandro already did it, so I think I'll just skip it. Again, just I like to re-thank again our company mentors, Javier, Oliva, Ines, and I don't remember the name of, and Pablo. So thank you, everyone. And then the UPN side, Juan, basically, and Natalia, I don't know if you're there, so thank you, Natalia, for your support. So what's the definition of this project? So you see there, what's the definition? So it's basically developing an analytical model able to optimize the performance of a bike sharing system. In this case, Barcelona. We'll talk about Barcelona a little bit now. How are we gonna perform this? So basically crossing data from driven vehicles and maintenance recommendations, what we call the parameters. And we've already focused this project in the city of Barcelona. So this is gonna be a digital twin. It's not gonna be a general digital twin. It's more like a tailored suit for the city of Barcelona instead of a pret-a-porter digital twin. So just to understand what a bike sharing system is, and specifically in Barcelona, Barcelona is the second largest city in Spain, 1.6 million population. The plot or the land is like about 100 square meters, and the longest distance between the edges of the city is about 15 to 20 kilometers, and the difference in height is like not even 10 meters. So if you could understand, or if you see that inside, it's like Barcelona is like the perfect city for a bike sharing system. These sharing systems in Barcelona were implemented initially like 20 years ago, so they are kind of mature. So what we're trying to do here is to polish a little bit the existing system. So where are our main objectives? So you see there, when we first talk about it, we said what we're looking for exactly, because Barcelona already has a system, it's kind of okay, it works pretty well, it's mature. So how you can improve the system, or what the city is looking for. So you see there where the main objectives or this Capstone project. They're gonna be focused on like bike availability, that is like how to provide a better system for customers, the cost reduction, just trying to minimize the rebalancing movements, and trying to minimize the, let's call it, the human side of this process. And by all means, we'll achieve a better user or customer satisfaction, sorry, a more sustainable system. So how to do so? So the technical objectives were like, we need to predict, to first make a prediction based on the existing data, and then optimize for the future that model. So this is basically what we're going to start talking about now. So what's the methodology that we've tried to apply to this? So you see here like a chart. There are 6 steps that I think this starts to be really known for all of us, because we keep repeating pretty much the same for all the digital twins. That is basically you have to evaluate an algorithm that, in our case, the algorithm or the parameters to be used have to be defined by checking or just assessing all the 16 tenders that we have in all the cities, in this case in Spain, just to find the more specific or the most crucial, critical parameters to be used. So the evaluation of the algorithm is, what is the parameter, what is the data that I really need to use in my model? Then we go to the coding part, or the process of just trying to develop something simple, like the first algorithm. And then we realized, Alberto realized specifically, that all this data in this case, or in general, because we need to see things because we are engineers, so we need the visual part. We realized that we need some kind of interface that's showing us what's going on with this data, because if not, we don't really have a tool to know if this is working properly or not. So this is the tool implementation for the visual evaluation, and then the parts, or the steps 4, 5, and 6 are basically training, evaluation, again validation, and then the final implementation. So this is the phase, and here the next 2 slides are just like a little bit a tip of this research on where we're looking exactly. So once we know the methodology or the process to be followed, we just try to think about like the software and the tools. And I think here is, again, it's pretty much the same. So we have this side that is like the background layer that is based on, you see there Python or tools that is like an API of Google to optimize Python. Then we have QGIS, that is basically for location services and for visualization as well. And then we have Qt, that is a specific package that we implemented just to polish all these process. So this is the schedule, or the plan that we initially prepare, and you see there I just explained. And here you see sorry, that my fault. The last post is July 2024, but I should have like September 2024, yes, for this presentation that is taking today, that we are having today, sorry. So here I'm gonna pass it over to Alberto, just to go more to the technical slide.
Okay, thank you, Ivan. Okay, well, I'm going to speak about the development, the phases of the development, and the results that we have with this DT prototype. We have made a prototype as a minimum viable product, and at the end of the presentation, we will show some parts of this DT. The phases of development start with the data collection and processing of that data. We search the origin of where to take information to apply for the analysis and the prediction optimization we want to make. With that data, we need to model in the physical systems. Now we have data, there are numbers and some variables, but these represent some physical concepts that we need to modelize through these digital twins. Once we have the modelization made, we take some simulations. So we have to implement that simulation in order to see the results in this beginning of the development. With that simulation, then we did make a validation of the results and verification if the digital twin give us the information we wanted for our operation process. If not, then we have to come back to the modeling phase and change some things in order to pass this validation and verification. If it's all okay, then we design with that the prototype itself in order to convert this like an application to use. For the first phase of the data collection, we have find three main sources. The most important maybe is the historic data that we have. We have collected from the open data web from the Barcelona city, and they have data for all the year, several years of the use of the bike, with the state of the stations, the available bikes and the available docks for park the bikes. That data comes in a CSV format. It's a plain text at the end, and it's all compressed in a file. That file we need to go there and download. And with that data, then we start to work. The data is about registers of the situation of the station. It's 5 minutes. They have information about the station's ID, the total free decks, and the total available bikes, and a time stamps to know the current time. And also we have another file that is the inventory, when you can find for that station ID what is the name given for the authority to the station, also the localization, and the total decks for the bikes. That data must be cleaning in order to erase data that is not necessary, maybe and all the station that is not in use at this time, so we don't need it to perform that analysis, and also check the integrity of the data. Maybe there are some mistakes because it's a plain test. And with that data, we make some processing because we don't need, for example, data each 5 minutes, because our analysis is for a 1 hour period. So maybe we need to aggregate, and then we have the final data we can introduce to our model. Other data that we can collect is the current status of the bikes for this moment. For example, if we go to that URL that put there, they will show you the current state of the stations in the city of Barcelona. That comes in JSON files in a standard GBFS format. This is a standardization for that type of mobility data. And also we need information about the situation of the streets or the buildings, or all about the background information to show with the stations. With that, we can use vector tile maps. That is a kind of maps that it can be shown in real time. So you don't need to. You have to connect to a server, and they give you that information. And if they change the information of the background, you take that information also in real time. And without data, and the modelization phase takes only, we have 2 physics elements, the stations and the vehicles that we will use to relocate the bikes from from stations that are full of bikes to stations that doesn't have any bike. And the predictions is about the number of bikes available and the number of dogs available for the bikes. The optimization is about the road that we have to follow to take the bikes from the full bikes stations to the stations that doesn't have bikes. And so we as you can see, you have the current status bikes that go to a database and also go to the prediction phase with among with other data sources like the weather or something else in order to make a prediction. With the prediction and the optimization model, we process that and we show the data to the company for perform that relocation. So we have 5 models. One is the first is the prediction model that takes the historic data and predict destination for similar characterized conditions. Day of the week, months, or meteorology, etc. The optimization model launch the UR tools, algorithms, and obtain routes for the vehicle's teams. That is what we are looking for. Then that information we have to present to the user, and for that we use KT and QGIS. And also we have another 2 models. One is for batch analysis. That is for to perform more than one single optimization at one time. If we need to take other or analysis and studies for studies purposes, not just for operational concepts, this is the model. And also there are also auxiliary models for some tasks that all the models needs that are put in an auxiliary model. This is the correlation that there are all the digital prototype you can find here is free, it's public, so you can download that at any time. It's in GitHub, and this is the correlation between the functional models that we have talked before and the Python physical files that you can find in GitHub. Okay, the prediction model. The prediction model that is in this prototype is a simplification of the prediction that we take for all the historic data. The prediction model is for only current data time. For example, if we take a prediction today, now, the digital twin can perform with a proper configuration a simplified prediction. That are the options that we have in the configuration file. They try the prediction like a constant demand, so the difference found between the status data between 2 consecutive queries are taken as the parameter prediction for the current period of analysis. There are 4 more configuration options and as many as one can program. The optimization model, that is the main part, it uses the Google Earth tools. Also, it's our algorithms that are free to use. You can find also in the web. And you need 3 main parameters. One is the time limit, the solution limit. So they limit the number of solutions generated during the search, because the Earth tools is taking different solutions and they compare them. So the combinations are very huge. You have to limit this because for the capacity of processing and the time processing. And also the limit in seconds is spent in the search for our tool. Also, it depends on the algorithm. there are a partial limit in second also for each local search neighborhood. And these are the algorithms used for all tools inside. It's also a part of the configuration, and we have tests of the algorithms inside to see which fits better to our objectives. They can be also changed in the configuration file. Normally, the path cheapest arc is used. This is the presentation model, and this came with the OSU4W distribution. It's also for free. You can find here, and with this we can design the front end to use for the digital twin users. So at the end, this is the presentation model. This is our prototype. And also the information that is shown in the prototype can also be shown in any QGIS desktop installation, because all the information is keeping in shape file format. So at the same time, you can use the digital twin. You can also see the results in the QGIS. The processing model. This is the normal processing task when you perform optimization from the graphic user interface. The processing model first has to create the data model to use for the optimization. For creating the data model, we have to generate estimated demand. The demand is for each station what number of bikes it needs to comply the KPI. So if with the option of real time, they do this with the current data at this moment. So they load the status data from the internet, and with that go to the prediction phase. If it's not a real time optimization, don't load the status data. And the prediction phase also loads the prediction data. If we have prediction data for the time we have generated, it loads it, and if not, it generates the prediction data as we've seen before in a simplified way. And with all that, we have the estimated demand that comes to the optimization. With the optimization, applying the OR tools, then we go to the presentation, and that's the flow process. The batch processing, as we told before, this is all for the operation level optimization. That is the normal use of the digital twin. For the present, we need to know what to do the next few hours with our vehicles, and we perform an optimization, and the digital twin shows what we have to do. But in other levels, like tactical or strategic level, we can use the historic data and perform optimization in background with a lot of simulation to have more information concerning if we need to increase or decrease the number of dogs in any station, if it's better to take more numbers of vehicles teams to relocate it, or also if where is the best place to put the depot station for the vehicles to start the routine. The simulation implementation. This is the sequence of steps. This is the digital twin. So we have an option to select the number of simulation steams that apply. We have 2 vehicles, 3, 4. This is the power we configure that. Then we can change the init station points for any vehicle. Then fits all the stations to the same point that is configured on the configuration file, or going each and select in the map where is the starting point. Then we have to fit the maximum time available for the vehicles to relocate. That comes in minutes, so we can put 10 minutes, 20, 30, any time we need. Then we select the story. Then if we If we select real time, we finish the configuration here. If not, then we have to select the available historic data because the digital twin perform a search inside the folders, recognize the files of historic data and appear here to the option. If we want to perform a simulation from something in the past. And at the end, we run with the button, the optimization, and the results appears in this window. So we can see the routes for all the teams. Team number 1 from station ID 1000 with 0 demand in the station, and the load in the vehicle is 0 because it's the beginning, it's normal. Station 352 have a demand of just 12 bikes. So we have the vehicle put the 12 bikes inside. So now the load is 12, and you can follow the steps that will follow. Also, this is the resume of the KPIs before and after optimization. KPI without bikes 99 for an amount of 505. And without those, 24. After the optimization, 0. And the 2 steps at the end is only for showing the results. We can show anything involved on the optimization in the map. If we mark a per the road here, like this is number, I don't know the number of teams. This is another. And also we can identify the information at each station level. So we have the available stations and the available logs before and after, and the KPI related only to this station. So validation and verification. The prediction stage, we take a validation of the data. We take an example from this day, an interval of 2 hours. With that data and the real and the predicted, we have a lot of difference. But if we mix the interval in a 2-hour interval, the difference decreases to 10 bytes. And this is the different histogram per each station. So there are, for example, 34 stations that are perfect. But there are a lot of more that not fit the prediction with the real data that we show later. The optimization stage, we have we can perform a direct optimization to see if the results to see if the digital are running okay or do something strange. This is a very simple validation. And without a video demo, but I will make a presentation, a direct presentation of the model at the end, so we don't show now the video. And also with the batch processing model, we can have a validation. For example, we have 4 variables in all this process. We have we start with the KPIs value we want. There are 2 KPIs. One is the dogs KPI, another the bikes KPI. We have time operation involved on the optimization, the number of vehicles, and the station departure of each vehicle. So if we change, for example, for 3 different stations, station 334, 1388, we have these results. So, for example, there are for a KPI of 0.1, if the vehicle starts in the station 34, they need around 50 minutes. But if they start station 388, they need more minutes. And from all the validation, there are 3. We need to define a algorithmic function to manage the different situations, because there are a lot of combination of starting points. for example, if we have 10 vehicles, we have 10 starting points, so there are 10 variables. But if we have 20 vehicles, we have so the combinations are a lot. So what we do is aggregate. We have a function aggregate. We simplify with all the vehicles starting for the same point, and we have three validations that we can perform. So the number of stations that for the selected number of teams or vehicles reach the required dock KPI in function of the operational time, or the same in function of the number of teams, or the dock KPI. We will show this also in the results part. Results. So there are some examples. With one vehicle, 60 minutes, starting from ID Station 1000, that is currently the depot of the bike sharing system in Barcelona. So this is the route for the vehicle, and what our tools say that is the best. And the stations in red are stations that don't comply with the KPI, so they have no bikes or no available docks. And this is another sample analysis, changing some parameters, starting for the same point, but now we have two vehicles. And well, you can show here the route and also the KPIs. And another two analysis results, for example, 3 vehicles. There are 1 third vehicle, but not appear in the screen because you can zoom in or zoom out, but with this matching doesn't appear here. As 70 minutes, so some examples. And this, for example, 12 vehicles. I put this because it's what we need to reach zero, all the station optimized. We need 12 vehicles with 90 minutes, because if you see the other performers, you will see that there are a lot of stations that are still under the required parameters. And then some steps with analysis of the results. The 3 performed that we have told before about the validation appears here. So for example, the number of departure stations that require a specific operational time to reach the required dock KPI are here. So this means, for example, there are about 42 maybe, 42 stations that for this KPI need 1 hour if all the vehicles start for that station. There are 130 maybe that requires 1 hour and 125. And if you sum all the stations, the total is 505, because there are the total stations involving the bike sharing in Barcelona. The other 2 analyses that we can perform is the same, but in this case we fix the time, and what we're trying to find is the number of vehicles needed. And for example, as you can see here, if we have 4,000 seconds to perform that, there are at least 50 stations that it doesn't matter the number of vehicles involved, they never will reach the required KPI. And the last analysis is this one. So here the parameter is the KPI value. So we change the KPI value requirement. We will find these different number of stations that complies that. In green is the dock KPI, and blue, light blue, not appear here, but is the bike KPI. And the limitations we have found with this digital twin is concerning the QGIS, has been developed as say here as a standalone. it allows a lot of things for the implementation. But on the other side, the processing and presentation tools that are also incorporated in the QGIS desktop application, we don't have in the digital twin. That is why in the beginning I show you that you can also show the results in QGIS desktop application, and you can use all that. Also, there is an option to develop the digital not as a standalone application, and doing as a module inside the QGIS toolbox as a plugin. So you will have to run the QGIS application, and then inside the QGIS run the plugin of DT. The other limitation concerning our tools, okay, the vehicle start. If the vehicle starts in a station that currently have a demand for bikes, it never finds a solution, because never can never return to the same station with this algorithm. So that station will never reach the KPI. That's a limitation. Of course, if we think about any other kind of implementation, we will reach a solution, but it's not doing in that version. Concerning the Google API use for the time matrix, the time distance matrix. Well, this is a free API, but it's limited to 100 requests at the same time. But if we have 500 stations, you have a matrix of 250,000 requests. So as you can see, if you only can make a request of 100, you have to make a lot of requests. So this takes time. So and the second limitation is related to the cost, because there are also a cost. Is free to use, but not is free in cost. In a trial, you have you have a limitation, and you have a price for any request. So at the end, we use a static time distance that is fixed, but in real, it's not the time between the two stations is not the same at the morning that at the 2 p.m. for example, and it's not the same on Monday than on Wednesday. But we fix that time for this purpose. Well, we will use Google API. We use other APIs, for example, OpenStreet. But at this with this prototype, we choose at the beginning Google, so this requires a change. And concerning the implementation itself, the detail actually makes a simplification by only taking stations that can be visited by vehicles. That means that in the beginning of the process, the stations that are okay with the prediction from the prediction model, the vehicles never go there. It's a simplification problem. For example, if we have only 80 stations with that needs to be relocated, that are the only stations that are going to the road problem. But in real situation, maybe is good or is more optimized or more efficient to visit any intermediate station, to leave some bikes there or to pick up some bikes there, because that gives us a better result. But with this simplification, we will never know that. And there are also no continuity between simulated cycles. For example, if we simulate the next hour, with the result of the simulation, we want to perform the subsequent hour, the vehicles starts with bikes inside the relocated vehicles, but this is not contemplated on the digital twin. Each cycle is independent of the others. And well, potential improvements for the future, like data very fast. And we can adapt this specification. We can introduce parameters related to the calls. We can adapt the background for use as command line for using for external scripts and integration with other platforms. There are an example of integration that we made before for other course in this master. For example, to Grafana, to see that. A panel where we can see something similar that we have seen in QGIS. And another possible research is about a integration for data mining. This is the total combination that we have currently with taking care of the number of vehicles. This is the number of combinations of visiting routes that we can find, and also more than one category of bikes, because currently in the bike channel in Barcelona, we don't only have electric bike, we also have mechanical bikes. This is not considered here. And maybe a fast show of the prototype and then conclusions. Okay, this is the digital twin we have seen before. With this, we can change the themes. For example, to see something, we put only 2, because maybe if not, well, this is data from any before simulation. This is the base map. We can show through QGIS also. The rotating time 50 minutes, and we can perform real time, for example, or showing a historic. In red, there are historic data that we have predictions, so we can choose one of these and perform the optimization. It's here. Sorry, this is I don't have the mouse, so I cannot zoom very well. Sorry. Maybe. Well, you can choose some parameters. Now we can show all the stations. Only stations to optimize. That's one in red. Only the optimization stations, etc. And also we can change, for example, all the stations. We can show change the starting point. Example. No, without the mouse is a little, because I need the red button, the right button, and here I don't have. Well, here. Well, the justification or change, for example, I change for team number 2, and I perform another optimization about 60 minutes, and we change the time period with 3 teams. And this is another example of a result. And also we can put real time, and if the connection is okay, it will perform optimization taking data from this time and the prediction, the simplified prediction that we told before. Well, this is the data. This is currently what we have in Barcelona now, and this is the optimization that is made. So, okay, this is.
And then just to wrap up very quick, a few conclusions that we have from all of these analysis. We realized that this is a kind of a simple tool, but with a great potential. So perhaps in the future, it could be like really scalable and it could be boosted to something really, really important. No? So that's what we think. The second conclusion, I think, is the something really simple to understand, that is like if we can or we manage to standardize this app or this process, you can just copycat this to every bike sharing system in the world. So it could be really, really interesting. The third conclusion is more related to the time and cost management, that we feel that perhaps with the right people, we could just speed up all the process and make like a further improvement. So yeah, I think that's all. Sorry. Thank you.
Thank you.
Thank you, Alberto and Ivan. We have just time for maybe. Sorry. So we move to. Yeah.
I got many questions, but Matthias said I just wait when I leave that one. I was thinking about what about the potential profit that you could get from this application?
We haven't made the calculation yet, but based on the distance we save by just relocating or calculating the distances, I think it could be like important, but we haven't calculated yet.
Non-technical, what was the part which the program had you, the competence, programming part or modeling part? What inspiration did you get the digital education program? I guess it's not only from your previous.
Not only for this.
Yeah.
Difficult question because
so the mixture of them, so multiple courses help you.
Yeah, of course. I think it's because the program. I'm less familiar with the programming. I think Alberto made most of the programming, but still I could at least understand all the models, all the train, all the validation process. And for me, the inspiration, or what I'd say, what is the best outcome for me, it'd be like to understand how to manage, or at least a very little, how to a process can be done, and what is the right people to perform that task. Because at the end of the day, I think for me it's the most important, how to link each part just to have something that it could be fruitful.
For me, it's actually it's not only to okay, I want to do a digital twin. I want to find a program to fit my digital twin that I seen before, and change that for now. Okay, I have a problem that I have the digital mind in my mind, and I can use that because before the master maybe don't think about a digital twin, and now with the digital, this one option to solve that problem. Maybe I use a digital twin, or maybe not with other things more simplified things we can do to solve that problem. So for me, that is a more top level of
feedback. Yeah. Thank you. Thank you. And then just the last comment from the supervisor. Everything was perfect.
Oh, yes, from my side. In fact, I learned a lot from them, from Normon, a lot of because they are working. The problem about bike sharing, it is a bit close to me, because I use bike riding usually. So, and I hate when there is not a bike but I despise when I am in a hurry and I cannot leave the bike where I am. So it is a very useful topic, and I know I've learned a lot about the programming and about project management from them. So perfect for me. Oh.
Yeah, just to say thank you to Alberto and Ivan, because it has been great to to exchange this problem with them and to discuss the potential solutions. We are implementing this the product related to this tool now in 2 cities in Spain, and the conversations we had with them were very inspiring to do so. So from our side, it was also great to be involved with them. Yeah.
Yeah. Thank you.
Lo de la bici, tal vez.
No,
O-
con la primera, la primera carátula. Tienen los nombres y tal.
Ah,
No, o sea, yo decía esta. Esta, ya está.
eso.
Espera para la foto.
Ah, yes.
We will keep in a hurry. Antia. So we stay with the HDMI because they need it for the picture, but you can install.
Okay.
So how many do you have enough for?
So is it,
So that's for the microphone, for Zoom, because people
Okay.
don't hear you if you don't use that.
okay.
So you need to this port. So you need
Okay.
yeah, is it okay
I
for the
can-
picture? Yeah, take it up. Like that's also. You can take your
This is
inside. Test. I think it's working.
You think so?
Let me just check. Where is the
What is this?
this is option, the option panel?
Ah, in Zoom.
No, maybe it's okay, it's working. We just need to close it. We can close it.
Yeah.
Just wanted to check that it is working. Or maybe exit the presentation and we start it again.
Wait, yeah.
Don't know where is no, this is on the other screen. Yeah, can you move your mouse maybe to the second screen?
Yeah, but
Yeah, and you can just close it. Close the display. Yeah. Okay. To go back and share again. Sorry.
So desktop one is this one.
Yeah, share it. You have to accept.
Yeah. I was thinking.
And we will. And you have to just go back to PowerPoint and put it in screen in the like lecture mode. You can yeah.
Is it because there's
No, it's okay. It's fine. Look at my computer.
I am.
Turn in the middle. Yeah, I have the attendance in the list of.
Because if not, they are not going to see the. I mean, they're going to see the other side.
I guess. Look. So I think it is working.
Yeah. But no,
Ah. Because there are two screens.
Yeah. So I'm gonna move.
Yeah.
And the question is, this is the.
You have to go back to the presentation and try it.
This one and the
Laser, yes.
Yes, the laser.
Don't use the little one, but just the arrows and. And you have the microphone. You have to give the microphone to Patch.
Yeah. Okay. It's okay.
And that's another thing. Oh yeah. Okay. Okay. Just in case. I think everything is fine. So we don't need this one. And I will keep it for the questions.
Okay.
Okay, we wait for Patch and start. If you can do it in 35 or 40 minutes.
I'll be quick. I'll try to be quick. I don't.
And maybe you need to give the microphone to Fernando to introduce.
Okay.
Because you will pick up. Pero no te Pachi. O Pachi va. Ah, pues ahí va a hacer la operación. ¿Está expliqué?
Sí, o sea, es mi pero. Ay. Yo pienso que ya van a dar las etiquetas, pero bueno.
Estamos.
Es una organización. Ah, digo la banda blanca esta del soporte.
No.
No, digo la de arriba, o sea, como vuelve.
We are going to start with the last Capstone project of today and of the whole master. I don't know how to start with this presentation because it has been a tale of pain, of fun, huge work, and I believe hopefully you realize that it's final success. You will enjoy the presentation today. We started with a very promising project about the optimization of traffic in a maritime port terminal. We then realized that the data that we considered that were going to be made available to us, they went at the end. Then we thought the proposition and moved to a very ambitious project that I will invite whoever is interested to develop in the future, which is the analysis, optimization, and improvement in general of what we call in Spain the Operación Puerta del Estrecho, el Paso del Estrecho, which is all this transit of people coming from the north of Europe that go down to particularly to the north of Africa, to Morocco, and that somehow collapse in 1 week, 2 weeks, the highways in Spain, starting from Belgium, France, Spain, and then they all collapse into the port of Huelva, Gibraltar, and creating a very complex situation. Well, we found another kind of travelers there, finding the data. In some cases, they were protected. That's understandable. And then after 2 falls, where we had learned how difficult is it for an engineer to find the right data, and that is a big learning. And thanks to the spirit of Antilla and Pachi, it's incredible, the spirit and the eagerness to learn and to take advantage of the opportunity that they have. And also thanks to the flexibility of Ineco with Rodrigo and of Javier jumping into the process, into the project. They found a project that really meets what they wanted to develop. And well, I'm very glad to make this presentation today because the results are absolutely applicable to the real world. And I really hope that you will soon be presenting them. Thank you very much to both Ineco and Nomon again. Please translate this and transfer this thanks to the innovation team of Ineco, that they have been supporting us from the very beginning. And well, what can I say of Nomon? You are our big joker. And finally, let me also thank to Javier. Javier Baca is the coordinator on behalf of UPM. He has also shown an enormous flexibility. Javier is a researcher at the ports department, and he has moved all his coordination capabilities to end up coordinating a project that doesn't have to do much with that, but still we need it and use his coordination abilities. So the floor is yours.
Thank you very much.
Thank you, Fernando. Okay, hello everyone. We are very excited to present our Capstone project. Thank you for the presentation, Fernando. That's a very good summary of what has happened during the last 6 months. I like the idea of the joy and pain. So, well, my colleague Patty, well, you can introduce yourself.
Yeah, well,
Patty.
I think that everybody knows me, no? I am here in this course, okay? Because, you know, I like to speak a lot. And, well, I want to thank also to Fernando because when we were in this crisis, because of the topics, he always be there and help us to try to solve the problem. So this was very important for us. We want to thank also to Javier for the flexibility and support that he was on this trial. Rodrigo and Javier also for his help. They when we explain the problems, they understand the problem and they give us always solutions. So this is also very important when you try to do engineering things. Okay, so thank you very much. Without you, nothing was possible. So Fernando is the same. So thank you, and hope you enjoy with this presentation. That we like to do a lot. We have a good work. We do a hard work, but at the end, it deserves all the work, for sure.
Perfect.
So thank you.
Thank you, Patty. So let's start with the presentation. Our Capstone project is called Eventful Madrid, developing a predictive model of mass events impact on mobility within an urban digital twin framework. So let's start. If it works, suddenly wait a second, sorry. This is the let me see.
It must be loud.
Yeah. Okay, let's see. Okay, now works. Always have a second pointer. Okay, so Madrid has seen a significant rise in the frequency and scale of mass events in recent years. This is due to the fact that Madrid has become an international well-known hub for mass events. And well, has been, there are a number of factors that explains this. First is the event-based approach to tourism that the city has, the huge infrastructure investments that they have done in the recent years with stadiums, fair venues. And the third one is around that this has been combined with business appeal of the city, its strong sporting heritage, specifically on football, and finally the extensive network, transportation network of the city. So let's deep dive a bit more on this. We started mapping the events throughout the whole year to understand the different patterns of the events. So as you can see in the screen, we categorize the events into the type of event: football, fairs, bullfights, religious procession, and so on. Then we categorize these events in the number of assistants and the duration of the event. So as we can see in the screen, football, for instance, football matches and fairs are year-round, with a small break in the summer. We have the warm weather springs the sort of festivals and music concerts in the summer. And then we have two seasons of bullfighting, both in spring and autumn, among many other different events that we will be analyzing today. So we then map these events into a calendar. So we have this diagram which has mapped all the period of analysis from January 2022 to May 2024. And this mapping of the events has been done. The diagram has mapped the events week by week. And as you can see here, it shows a concentration of events around May and June, with a clear drop in summer. So we started with the exploration of these events to better understand the patterns. And as we can see also in the screen, we have identified an annual growth of around 20-25% of the number of events from 2022, also due to the pandemic. The next question is, okay, we know when these events take place. And now the next question is where these events take place. So we identified 13 venues in the city. Some of them are stadiums, such as the recently renewed Santiago Bernabéu and the Metropolitano Stadium for Atlético de Madrid. We also have some other sporting venues, such as La Caja Mágica for tennis. We have also Patios Deportes, and we have, of course, Plaza de Toros de las Ventas for the bullfighting. Then we have, of course, some open spaces. And these open spaces normally host festivals and different kind of activities, such as demonstrations, for instance. So we have the book fair in the Retiro Park. We have Pradera de San Isidro hosting the largest popular celebration in the city. And then we have some smaller open spaces, such as Parque del Oeste, Tierno Galván Park, and Cantarranas Field that host some of the bigger, some events around like music festivals. And finally, we have the Verdrola Music Space, which is a recent open space that has a capacity over 100,000 people, a capacity of 100,000 people. So, okay, so the selection, the location of these venues has determined the selection of the districts of analysis. Why is this important? All the mobility data that we have processed and analyzed is at a district level. This is like the lower level of the disaggregation of the data. So this has determined the selection of 12 districts out of the 21 districts of Madrid. And the interesting thing is that we have a variety of districts. Some of these districts being having high commercial and high leisure profiles, very central districts such as Centro, Retiro, or Salamanca. And then we have more residential districts such as Carabanchel, Usera, or Puente de Vallecas. So we wanted also to have this comprehensive approach to the different districts that we are analyzing to have a more rich analysis, a richer analysis. Okay, so now that we know when and where, the question is, what is the issue with this data and with this project? So here, the issue is that some of these mass events are maybe, some of them are inadequately planned, or some of them were not initially anticipated as mass events, but for some reasons they became mass events. So implying that for instance, you can see in the picture, the drone show in Casa de Campo or the Madrid Christmas lights switch on in 2022, which generated huge crowds, which could entail some risks. So the issue here is, and we started thinking, okay, how we can assess and measure these mass events. So we thought about what is the key factor that the attendees of these mass events have in common. And these are the smartphones. So what we've done is we use all this kind of devices generate a wealthy, rich data in terms of real-time data and very accurate, that is very accurate in terms of geolocation. So these devices interact with the communication antennas, generating some events named as call detail records or proof data. So all this data, thanks to Norman, it has been processed into and converted into the origin destination matrices, the classic tool for transport analysis. The Ministry of Transport, MIDM, has made public this data as the open data mobility, so at a national scale. So we were able to analyze, to use this data for the different analysis. So let's go back to the events that we were mentioning. So in this picture, well, stay with me because we are going to see later what this data means, what this graphs means. Don't worry, we are going to explain that better later. But as we can see in the pictures, there are clear peaks in mobility. For instance, in the case of the drone show, that showed that the expected 2015 people, 500 people expected for the event, ended up being more than 14 trips. So the data, so we just realized that the data was incredibly useful for analyzing this kind of events. So, of course, mass events have very positive impacts in the city. They generate, for instance, a lot of revenue in the city and has some positive impact in the city in terms of positioning, but they also have some problems, some urban problems. So the rise of these frequent mass events, sometimes poorly planned, it's been called and named by academics like identification. This term has also been adopted by some neighborhood associations in Madrid. Identification, the term means this increase in the number, in the size, in the impact of not very well planned events in the city, causing a number of different problems in the city. Some of these problems, as we can see in the screen, are the noise levels exceeding the official decibel limitations, vibrations in building caused by the buzz of sounds, impact on neighborhood, mobility due to the changes in the public transportation and traffic jams, the compromise of road safety, the accumulation of trash, crowds in public areas, the closure of public spaces during the mass events, and the impact of the lights and projections in the city. So as we have seen, some of these problems have already been rendered in a venue such as the Santiago Bernabeu Stadium, where it nowadays hosts over 200 events a year, which has led to some neighborhood protests and has ended up last week. They have postponed all the events planned for this year to the next one. So, well, I like a lot this image because these are the crowds attending Karol G event. They had like four consecutive concerts during 4 days, attracting over 240,000 people. And this is just the beginning because the first event of this type was with Taylor Swift in May. So the question now is, okay, seeing that this is a growing phenomenon, the question is how we can improve planning and coordination of mass events in the city. So the good news is that we have 3 clear enablers for analyzing this. That has provided us with the opportunity of analyzing these events. The first one is that we have the data, the mobility open data that we were mentioning before. So the Ministry of Transport has made available all these OD matrices at a national level scale. So all these matrices comprise it's around 3,743 areas in Spain, districts. And also they also include some regions in France and Portugal, summing up to 117 areas and a global area. So, well, thanks to Nomon, they have processed all this data and they have made that available to the public. We have specifically used the basic studies. There were 2 kinds of studies, the basic one and the complete ones. So we use the basic ones for this project. Secondly, we have the model, the AI model, the temporal fusion transformer. I will introduce it now, and then we will see a detailed explanation on the model. So the temporal fusion transformer is a state-of-the-art deep learning model that is especially suitable for this project, it allows the multi-horizon forecast using time series data, and including also some statistic metadata so that we could analyze all the mobility data from the events and cross that against the events data. And thirdly, we have the framework, the Madrid Digital Twin, which ties these all together. Madrid has released recently their platform, the Madrid Digital Twin platform, which has a number of use cases for simulations, for analysis, using in order to do short-term and long-term analysis. In terms of security, in terms of emergencies, they have a number of use cases that they are still working on. So we also see that there's a potential fit of the project within that framework. So the objectives of the project. The first one is assess the impact of mass events on Madrid urban mobility and develop an AI-based model to predict and simulate these effects. Within this first objective, we have some sub-objectives, let's call them. First is to collect and to create data sets, including daily mobility data, weather and mass events features. Second one is to develop visualization tools to identify these mobility anomalies and the geographic trip patterns linked to the mass events. Third, implement an open source predictive model using advanced neural networks for mobility forecasting. And finally, potentially integrating these results, because we haven't done that yet. If they are interested, we will be super happy to do it, to improve the mobility and urban service management. The other two objectives are create a methodology for analyzing mobility network data to predict mobility patterns across various urban settings. And finally, to develop a replicable framework that can be adapted to other cities hosting mass events. Okay, so now we are going to show you the methodology. We're going to explain it at a high level. First, we started with the data collection, creating two types of data sets that we are going to explain later. Mobility data sets, as we have already discussed, the mass events data sets, which were later processed using different scripts, and we end up having all these processed mobility data sets, which undergone exploratory data analysis process, which allowed us to create an advice to identify the relevant features that will be selected in the feature selection engineering step. These features will input the predictive model development. We developed two types of models that we will later explain as well. The global model, including developing a model that includes all districts, and individual models for creating a model per district. These models were also had some optimizations, and they passed also some testing and validation. Finally, we will propose some use cases development based on the data. So before jumping into the development of the project, we wanted to explain some of the considerations also to be clear on what kind of data are we using for the project. First is the when the time frame of analysis is from January 2022 to May 2024. This is the availability. This is due to the availability of the data of the public data on mobility. The second one is that one thing that is important to mention is all the mobility data that we are receiving are outbound trips. Is to say, and that's what we're going to explain now. We use outbound trips, which are the trips leaving from the event to any other place. And specifically, we also filter the data depending on the activity. So we filter all the data from origin as non-frequent activities to any other kind of activity in the destination. It's important to mention that the mobility data is categorized based on the activity of the trip, what is the activity that justifies the trip. So home, work, study, frequent activities, and other non-frequent activities. We also wanted to mention that we are including all districts in Spain, Portugal, and France in the analysis. And of course, to mention what we already have said, that we have selected these 12 districts. It's important to mention that the threshold of definition of what is a mass event is around 20,000 people. And this is determined by a legislation in Madrid called the Sustainable Mobility Ordinance. So this is the threshold that we have taken for the study. So we're going to explain a bit more on this outbound trip data. What you see at the top are different patterns on the trips. So we wanted to make clear two things. So in this case, you are seeing the different trips of people attending a football match, the Atlético Real Sociedad. So as you can see in the screen, some people leave earlier, some people leave after. The thing is that all the data, all the trips in the data sets are taking as a reference the origin of the trip. So all the hours specified on the data sets are related to the origin of the trip. This is very important because we could only analyze what was the origin and what is the timestamp of the origin of the data. So the thing, like for instance, people traveling from far away of the country, the window, the time frame will be much bigger. And so we take the data and we wanted to test this. So as you can see in this graph, there's a clear peak after the football match, showing that a high concentration of trips after the end of the trip. And what does it mean is that we have a time frame of 2 hours to determine which trips are attributable to the football match. Whilst if we took the inbound trips, that time frame of analysis will be much larger. And of course, it's not easy to attribute all those trips to the football match. Some of them could be attributable to other non-frequent activities of the districts. This is important to mention because from this moment on, all the data that you're going to see are outbound trips. So for experts on mobility and transportation planning, please take this into account when you see the graphs. So now we start with the development of the project. We started with the data collection and processing. So as you can see here, we started collecting all the data sets from the basic daily studies. We had have 912 days. And we also took as a reference the district centroids in order to be able to then spatialize and to map the destination of the trips. All this data, we processed we processed 4.45 terabytes of information, which is considered nearly big data and was a huge challenge for us processing all this data in terms of computational resources and in terms of storage of the computers. So we took these attributes from the data: date, period, origin, destination, origin activity, and destination activity, and the number of trips. So what we've done is we filtered the number of the districts that we were interested in for the study. We filtered the non-frequent activity, as we said before. So we end up having this data set about outbound trip data. So we have two key data sets in this project. First is this outbound trip data. And then we needed to collect the data on the mass events in the city. That data does not exist. So we had to do it from scratch, from zero. So, with endless Google searches. So we collected for each of the mass events from January 2022 to May 2024. We collected the timestamp, the event district, venue, event category, the impact, if it was regional, national, international, which could be an interesting feature for the model, for the predictive model, if it was open air or not, and then, of course, the attendees, the number of attendees. So we had these two data sets. So we explored these data sets through the explorative data analysis. So we wanted to see, well, we had to match the timestamps, had to match the districts. So at the end, the question is there a relation, or are we able to relate the number of trips with the attendees? That was one of the questions. At the end, the objective variable that we were analyzing in the project were the number of trips per day and hour. So how we did this? Some of the mass events could be more or less easily identified, but most of them were very difficult to spot in advance. So what we did is that we created this app. This app allows you to introduce the week, introduce the district, and it gives you two kind of visualizations, and a daily visualization per hour and a view per week of the total number of events and the districts of destination. So as you can see in the screen, the process is that we have been reviewing week by week all these trips and all these mass events. So we did the analysis of the whole 12 districts during the period of analysis. So we have two clear peaks here. So we will see this. Well, this example is the optimistic one. As you can imagine, normally there were not those clear peaks. Oh, sorry. So we identified these peaks. We looked for it in Google, and we identified the different matches. That we saw that there were two matches here: the Atlético Real Sociedad and Atlético Feyenoord. So we collected all this data and we introduced the data in our data set. And this was a repetitive work that we did to end up having a big data set of mass events. So now we go to the exploratory data analysis part. So we want to show you this data from two different points of view. The first one is the exploratory data analysis per district, and the second one is the exploratory data analysis per event. So we have picked 6 districts to show you different patterns and different with diverse uses. So first one is Retiro. This one, Retiro, hosts the book fair, which is the district's largest event, accounting for the third of the annual trips in the district. So as you can see in the screen, we have mapped these black dots are indicating the mass events during the period from January 2022. So you can also see this band, like these strips in red and blue, showing the Christmas period and the summer period that normally entails a valley in the number of trips. So the book fair, as we can see, is the mass event with the highest impact in the district and has seen a 1.5 increase in mobility from 2022 from 2023. Second district is Salamanca. Salamanca, if you don't know, it is one of the districts of Madrid with highest activity in terms of commercial activity, leisure activity. So the thing that happens in Salamanca is that the main event here are the bullfights in Plaza de las Ventas. So the bullfights have are very close. The number of attendees is very close to the threshold of the 20,000 attendees. So what happens in Salamanca is that there are a large number of trips that related to leisure, like restaurants and so on. So we can see clear peaks in Christmas and in other dates. So in this district, for instance, the mass event do not have that huge impact as in others. Thirdly, we have the Chamartín district. Chamartín hosts Santiago Bernabéu. So as you can see in the graphs, many of the days with the highest mobility also corresponds to the days with the football matches and other events that are starting to take place in the Bernabéu Stadium. So, and what is clear, and after analyzing the data, is that if there's a football match, then the mobility of the district increase nearly like 75 points. So the fourth one is another is a special district. It's Carabanchel, which is a very residential district. Carabanchel hosts the largest popular celebration in Madrid. So as you can see in this graph, there are clear peaks when the San Isidro Fair takes place. So they overcrowd the district, and as if you are from Madrid, you can see that sometimes the transportation network is not prepared for that. So there's a high correlation between mass events and the number of trips per day and hour. And fifthly, we have the San Blas Canillejas, which hosts the Metropolitano Stadium, which accounts for most of the days with highest mobility. And we can see that the data shows that 79.46% increase in trips per hour when there is a football match or there's other kind of events like music concerts and so on. And finally, we have Barajas, which hosts the IFEMA, the fair institution in Madrid, which also represents a large number of mobility days in the district. The thing is, IFEMA, that they have many pavilions. So sometimes some of these events, the aggregation of different events in the district, although they are not considered mass events because they do not reach the 20,000 people attendance, also have an important impact in the district. Now let's jump into the exploratory data analysis per event. So we have selected a number of events that have been ordered chronologically. First one for the PSG fans is the Real Madrid PSG football match in 2022. So we wanted also to bring back the spatial component of the analysis. So as you remember, all the trips had this were included all the destination of the trips. So in this case, we wanted to see how diverse were these destinations. So as you can see here, people coming from Paris, people coming from other countries. I'm going to go quickly through all these different eyes because we have included, for instance, the Pride Parade, attracting people from a large number of different districts. As you can see, we also included a graph with the impact of mobility on this purple bars indicating the anomaly produced by these events. So the Pride Parade in Madrid in the Centro, the health system demonstration that took place in November 2022, that attracted people from very different districts in Spain. The Mad Cool Festival, which had a less impact from a variety of districts point of view. The Atletico Lazio Roma, also with a very, as you can see here, the football matches have show these clear peaks. The Manchester City and Real Madrid, and the Real Madrid Barcelona event. As you can see, many people coming from Barcelona and with clear peaks before and after the event. And finally, the Taylor Swift concert in May, which mainly attracted people from the Madrid region and people from Alicante and Valencia. So as you can see, this also demonstrates how the impact of the event. We have found that the destination was an important feature to determine and to be able to input that to the predictive model. So now I will give floor to my colleague Pachi that will explain to you the predictive model.
Okay. Thank you, Tia. Okay. Let's go to the interesting thing or the boring stuff. Depends on you. Okay. So that is the model. And what is the frame of the multi horizon mobility forecasting? Well, we are in time t, and we want to predict one variable for time t plus 1, t plus 2, and until t plus m. Okay, and for this we have data from t minus k to t. Okay, so
this is the problem that we want to solve. Okay, and in one click, we want to predict, to forecast that variable from t+1 to t+m. Okay, but what data do we have here? Well, we have the previous mobility. That it's a good predictor for the future mobility in time series. We also have data from the weather that we obtain from Madrid open source data, and we have features related to the time where we are. That is day of the week, month of the year, and also we have the official holidays that we can obtain from the calendar, from the official calendar, the labor calendar, and also seasonal periods. That is special periods where there is some official vacations there, but people get that period as a whole. That is, for example, Christmas, or for example, the Holy Week, or the 1 month summer, more or less, where the mobility change inside the city. Okay. And all these features that we have, we know them from the past, and we know them also from the future. So we have information to predict also from these features. Okay. We also have events information about the type of events, the number of assistants, and also we have this information from the past and also from the future. From training, we have from the future because we have the data, but in inference, it's an hypothesis that we have to take in account to make the prediction. Okay, and also we have the district that it defines the characteristics of the mobility inside the district. Okay, so this information we translate it in features to fit the model. And what features do we have here? Well, we have a time index that we use to have a ordered representation of the data. We have the mobility outside, that it's the mobility that we obtain from the Ministry of Transport, and we have now features related to the time. Okay, how hour of the day of the week. We have month of the year, quarter, week of the year, day of the year, if it's weekend or not, and this is categorical information. Okay. Then we have also information about the time, but continuous, because we try to say to the model that time is continuous, it's not categorical. Okay, so we have the hour cosine, we have the hour sine, the day of week cosine, and day of week sine also. We fit with the holidays, and also with the extended holidays, the periods, those periods that I spoke about, Christmas and also summer vacations, etc. And then we have information about the events. That is the event type. We have several event types that we have checked during this period of analysis. We have the football, rugby, concerts, festivals. We have bullfighting also, celebration, demonstrations, all type of these massive events that we can find in the city. Okay, we have the impact. That is, it can be national or international. For example, a football match between Real Madrid and Cádiz is national, but a football match between Real Madrid and PSG is going to be international. Okay, so we have the price if you have to pay for the event, and the assistance also. We know how much people went to the event.
And also we have the temperature and the precipitation, because sometimes that factors, for example, in Madrid in August is impossible to live because of the temperature. So if the temperature is very high, maybe people want to stay in homes, and also with the precipitation. Okay. So, and then we have the district where the event is celebrated. Okay. So these are the main features that we use to fit the model. If we have here the plot of the importance of the relevance of the features regarding the correlation with the target. Okay, that is mobility, and we can see that the hour of the day, the temperature, the if it's weekend or not, day of the week, assistance, event, and impact have a positive correlation with the target. And at the same time, we can see that the day of the week thing, our cosine and our thing is negatively correlated. If we analyze the feature correlation, we can see that we have some variables here that are correlated: the quarter, the week of the year, the day of the year. Nothing surprising, because are features related to time. Okay, and at the same time we have here the assistance, price, impact that are also correlated because they refers to the events. Okay. Here in the hierarchical clustering features correlation, we can find the clusters of correlated variables. And so we can see that those that characterize to the events are correlated. Also are correlated those related to the time. And also we have the mobility and the hour of the day that also are correlated. Okay. So in this moment, when we have all the data, we have all the features, we have all the information, we have to we should take some decisions, some choices for the model. Okay, yeah. So which type of model we should use? Simple versus complex, classical model versus state of the art, machine learning, deep learning. We have to take in account which models are using in other cities. And also, one thing that we should take in account also is the limitation in time and resources, that is computational resources. And we get the complex one, because life is no easy. So we get this, the temporal fusion transformer. Javier told us about this model. He gave us the challenge, and we get the challenge. And finally, we could do anything with that. So thanks, Javier, for this. And another choice that we have to take was the forecasting time, M, and the input data window. That is the information, the size of the information that we are going to feed the model. Okay. So here we choose 15 days for the forecasting time. We have to take in account that the frequency is hourly. Okay. Each hour we are going to have a prediction during 15 days, and it is a lot. 360 points of prediction in time. And for the parameter K, we decide that we don't know exactly how much time. So we are going to make some experiments to check what's the value of the parameter K. Okay.
we have to take in account that 15 days, we thought that is sufficient time for the management team of the council to make all the planification of the events related to security, traffic, etc., etc. That's we get this value. Okay, and at the same time, we have to decide if we want to train our model in a local district only, or for all the districts. Okay, so we call that local, that is trained individually in each district, and global, that is one model for ruling all the districts. Okay, so we have some benefits from one and another. For the local is good because it's adapt to local mobility patterns. We have a complexity reduction because the number of data that we have to train each model is less than global. Okay, but from the point of view of MLOps, that is the maintenance of the future applications, we are going to train and we are going to update 12 models. Okay, and the global, we have global patterns and generalization. That is good for generalize, but we are not going to get the local patterns. It's a more complex model because we are going to train the model with the whole data, and it's going to be easy to manage and update because there is only one model. Okay, so our choice is use both. Okay, we don't know what to do, so use both. At the same time, we have to decide the training, the validation, and the test set for the for our model, and taking into account that in time series we need that the training is where the closest as possible as we can to the prediction. But we also need a validation set. Okay, so we take as training from January 22 to March 24 as validation. We get from middle March 24 to May 24, and then for the test that is 5 only. Well, the test is going to be May. Okay. So what model do we use? We use the temporal fusion transformer. That is a model that was released from Google and also the University of Oxford in 1220. So it is a new model that we can use. There is no too much experience about this type of models, but we know that transformers are used for big companies for the most known companies, tech companies in the world. So, and as you can see, we have one related to civil engineering and another one here related to civil engineering, but I think that they are doing GPTs or something like that, no? But we have here Mistral, that is a French company. Okay, it's very important in the world of artificial intelligence. So at the same time, we have information about secret information about Transport for London that they use this type of model for making the same prediction than us. So this reinforces our hypothesis to use the model. So why this model is good for this problem? Because it's adaptable to different type of features that we have. It's designed to deal with temporal patterns, so we don't need to make a feature engineering with the model, with the information. Sorry, and we have multi horizon forecasting in one single shot. Okay, and has explainability also. Okay, this is the architecture of the model. One of the things that we have, we can input past data, future data, and static data. As you know, as we said before, we have past data, we have past known data, we have past and future known data in our data set, and also we have static data that is from the district. Okay, this model use variable selection to select the inputs and determine the features that are important. Also filters noisy features. Okay, we are going to encode the static information, and this information is going to flow from all the architecture. So all the points in the architecture are going to be informed about the district that we are working with. At the same time, we have LSTM neural networks that learn shown patterns very well. Okay, and we use attention, that is the main feature of the transformer, to get to learn long-term dependencies. Okay. And finally, the output that we have with this model is quantile forecast. Then we have the decision that we take of 15 days in advance, and we have to determine the value of K, how much it is. Okay, so we make some experiments, and we take as value 15 days, 1 month, 2 months, 3 months, and 4 months. Okay, and then we train some models, and we saw that we need, in some cases, exponential resources with time. Okay, we get until 4 months because our computing machines can't do anything with more time. Okay, so at the same time, the computing time, you can see that is growing exponential. Okay, so what happened with the loss? When we have a bigger period of time, we saw that the loss is less. So this is better for our model. Okay. But our recommendation is that if we have low computing resources, we should use K with value 1 because there is a local minimum there. But if we have sufficient computing resources, K is 4. Okay. So what we do? Key 4. Okay, we choose key 4, and this is one of the training curves that we use in this computer. Okay, this computer is alive today, but and this is the main libraries that we use. Okay, Python, PyTorch forecasting, Optuna for the optimization, and Macrolib. Okay, so results. We have the results for the global model and the local model. Okay, and in general, I can advance that local models, we have better results with local models, as we are going to see in the next slides. So normally, the global model adjusts well to the prediction, but the local, we can see that sometimes overestimates the values. Okay, and the local fits very well. In the case of Retiro, we can see that is capable of predicting the mobility of Madrid Book Fair. Okay. In Salamanca district, we have more or less the same. Okay. The global model doesn't work as well as the local model, and even the local model is capable of predicting the first bullfighting of the first event of bullfighting of the year. That is usually is an outlier. Okay. In Chamartín, in Santiago Bernabéu, what we have here is that local model overestimates concert events. Okay, as we can see, the global model, the local model also, but less. Okay, and adjust very well the football matches. Okay. Then we get another case from Chamartín, and we can see that local model works also better than global model. And even we have good predictions for the game, for the football match, but in case of concerts, doesn't work very well because we don't have a lot of information, because the event type concert in Bernabeu, we only have from, I don't remember, but April or something like that. So we need more data, okay, regarding that. And in Carabanchel, okay, we can see also that we have a good prediction for the model, and also in Puente de Vallecas. Okay, so this in the district of San Blas, home of the Atlético de Madrid, we also have very good predictions from the model, and even for events that let's say outliers also, like rugby match. Okay. So
I'm gonna be super fast.
toma.
Bueno. Okay, so we just wanted to end up with the use cases for the digital twin. So the first one that we see, we have generated these matrices, a structure in 4 modules. Firstly is the historical twin, which analyzes historic data from the model, so to have statistics and records of past events in order to understand the different patterns for future cases. The second one is operational twin. We have structured this in these four modules: the historical twin, the operational twin, the planning twin, and the scenario twin. And we have also put here in these columns the different fields that we see that there's some application. So even planning, transport, emergency, weather, etc. So so we have the historical twin, the operational twin with the window, the time frame that Patch explained, around 15 days, 1 month out. Then this data, this model can be applied to for planning twin with a GR out, and also for scenario teams in order to provide data for investments and infrastructure. So we're going to explain 3 use cases. First one is solving data gaps in mobility data. So nowadays, sometimes the telecommunication companies have some gaps in the data for some days. So the first application that we see is the Ministry of Transport doesn't have to use data that is incomplete. I mean, they can use these predictions that are more or less quite near to reality. So this is the first use case that we see for the data. Second one is localized marketing and destination analysis. So as we said before, we have all the destinations from the events. So one application is for promoters of events, to use this data in order to create advertisement and marketing in the different regions where the people come from to the event. The third one is integrating within the digital twin framework of the city. So as you see here, this is the architecture of the digital twin of Madrid. So we see that we can integrate our project within the data sources, including mobility, mass events. We can integrate also within the virtual representation and the computational representation with integrating the TFT model there. And then, of course, we see clear possibilities of integrating within the visualization analytics services with historic and forecast mass events data. And of course, this can give input to all the services of the platform. Here we also stated the different sectors to which our project can give input. So we have one more thing. So I'm gonna put this video first. I'm gonna pass it quickly. So we have this app here. Do you want to? Okay, let's go for the app.
Basically, this is an application that MVP that we built with two main applications. Okay, the first one is to see analyze the data from the past. That is that. Okay, we can select the time, the week, and we select also the district, and we can see, for example, in this case, we see the peak of the mobility, and at the same time, we in the application we have another module of forecasting. Okay, so we input all the information of the event, the day, the district, the event type, the hour, the end hour, the start hour, and end hour. Well, all the features of the event, and we can make a prediction about. In blue, we can see the mobility predicted without the event, and in orange, the mobility predicted with the event. So we can see the anomaly that that the event makes on the mobility, and also we have there the values predicted by the model. Okay, so we can take the decision about this type of predictions. Okay.
That's it. We can put well. One last.
Well, that's really one second.
Yeah. So I think like the key conclusions are clear. We have discussed already. The only thing that we wanted to mention is that we see clear next steps with regards to future research to improve the work that we have done. So expanding on data quality and quantity, which is critical to improve the model, to incorporate moderate attendance events, those between 5,000 and 20,000 attendees, and optimizing some of the model parameters to improve the model. So for us, the model worked quite well. The main problem there is the data availability.
Yeah, the lack of data for
exactly.
some events.
And just to mention that this framework, it's replicable. We see that it's replicable to any other city in Spain. Yeah. So we see high applications there in order to replicate this methodology. So that's it. Thank you very much.
Yeah, congratulations. I think they deserve to be applauded. So we have like 1-2 questions from the jury. Virgul, if you can speak to the microphone, please.
Questions.
Or comment or what?
Actually, comment because there's no questions for such a work. Did you clone yourself that you were doing this work? Did you clone yourself?
Very good question.
Well,
well, we didn't, but at the end, the secret of this, I mean, we have done, can we say, all this work very, I don't know, the thing is that we work together as a team very closely during the month. I mean, we developed this during the summer months, so nearly two months and a half. So while working as well.
Yeah, working very hard.
While working our jobs, professional jobs. So we base the secret to this is that we work as a team, talking every day, having sessions every day, being super aligned, being very practical, and we have
using tools, new tools.
new
also.
tools. We haven't seen it, but we used also tools for sharing communication. For instance, using Cursor to write the memory, using many different tools that have made our life easier. I say. So and being very committed to
the result. Yeah.
to the result of it.
One comment that like I would really push you to publicize this work.
Sorry,
To write an article about this work. But just don't put time in between. Just get it done, like in short period of time, because it's a great work, and you should get really good references, and also it's applicable to the field. Like find the market for it or startup, whatever.
Thank you very much.
Yeah, so I mean, I think we all agree. Like, we are very pleased by your work, but we are really in a hurry, so we have to stop now. Thanks again for this amazing presentation. And now I welcome everyone to go outside for the little lunch. Thank you.
Y ahora we need to take a picture or la ponemos con la pongo con el título.
Sí, no. Grupos. Foto. Can I take the group one?
Yeah, thank you and the sensor.
Yeah.
Oh. Ya acabado.
Yo soy solitario.
Claro, es que por eso te digo que han de comer. ¿Qué tal? Te iba a preguntar.
4 horas.
4 horas de clase. ¿Y qué tal?
¿Cómo?
Uy, me he quitado el micrófono.
Hay que sacar.